In an electrical installation, it's critical to correctly identify the service point and the service disconnecting means to ensure proper bonding and grounding, adhering to the National Electrical Code. The service point is generally defined as the point where the premises wiring connects to the utility supply. This is typically at the utility transformer itself or the point of attachment of the service drop or lateral. The service disconnecting means is the switch or circuit breaker that controls all power to the building or structure. It's the main point to disconnect power to the entire system. According to the National Electrical Code, specifically Section 250.24, A5, the neutral conductor must be bonded to the grounding electrode at the service. This bonding ensures a low impedance path for fault current, helping to clear faults quickly and minimize voltage rise during fault conditions. It also provides a reference point for voltage, which is essential for electrical safety and proper operation of equipment. In installations where there's a disconnect switch before the meter, that disconnect is not necessarily the service disconnecting means. The service disconnecting means is usually the breaker located in the meter can. Therefore, the bonding of the neutral and the grounding electrode conductor should occur at this breaker in the meter can. A grounding electrode conductor connects the service equipment, typically the neutral bus, to the grounding electrode. The grounding electrode can be a ground rod, a metal water pipe, or a concrete encased electrode, also known as a U for ground. The size of the grounding electrode conductor is determined by NEC Table 250.66, which correlates the size of the service entrance conductors to the required size of the grounding electrode conductor. It's crucial that the grounding electrode conductor is properly sized to handle potential fault currents. When installing the grounding electrode conductor, it must be protected from physical damage. The National Electrical Code outlines approved methods for protecting the grounding electrode conductor. The grounding electrode conductor should be run in a dedicated grounding electrode conductor raceway or use other approved means. Electrical metallic tubing, or IMT, is not typically considered an approved method for enclosing the grounding electrode conductor unless it's properly bonded at both ends, because if it's not bonded correctly, it can create an inductive choke, impeding the flow of fault current. The purpose of bonding the EMT is to ensure electrical continuity and provide a low impedance path for fault current back to the source. Both ends of the EMT must be bonded to the grounding system to comply with code requirements. This bonding usually involves using grounding bushings and bonding jumpers to connect the EMT to the enclosure on the grounding electrode conductor. It's important to understand the difference between grounding and bonding. Grounding connects the electrical system to the earth, providing a path for fault current to return to the source. Bonding, on the other hand, connects non-current carrying metal parts of the electrical system together to create an electrically conductive path. This path ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. Proper bonding is achieved by using bonding jumpers, grounding bushings, and other approved methods to connect metal enclosures, raceways, and equipment together. The size of the bonding jumpers is determined by NEC Table 250.102, C1, which is based on the size of the circuit conductors. In a three-phase 277/480 volt system, the voltage to ground is 277 volts, and the voltage between phases is 480 volts. This type of system is commonly used in commercial and industrial applications due to its efficiency and ability to deliver power over long distances with less voltage drop. When inspecting an electrical installation, it's important to verify that all bonding and grounding connections are properly made and that all components are adequately sized according to the National Electrical Code. Check that the grounding electrode conductor is securely connected to the grounding electrode and that the connection is protected from corrosion. Verify that all metal enclosures and raceways are properly bonded together into the grounding system. Using a multimeter, you can measure the resistance between various points in the grounding system to ensure that there is a low impedance path for fault current. A high resistance reading indicates a poor connection or a break in the grounding path. Always consult the latest edition of the National Electrical Code and local electrical codes for specific requirements and guidelines. Understanding and following these codes is essential for ensuring the safety and reliability of electrical installations. If the installation does not meet the requirements of the National Electrical Code, it's necessary to correct the deficiencies before the utility accepts the installation. The first step is to identify all areas where the installation deviates from code requirements. This includes ensuring that the neutral and grounding electrode conductor are bonded at the service disconnecting means, that the grounding electrode conductor is properly sized and protected, and that all metal enclosures and raceways are properly bonded. Once the deficiencies have been identified, develop a plan to correct them. This may involve rerouting the grounding electrode conductor, installing additional bonding jumpers, or replacing undersized components. Before beginning any electrical work, always disconnect power to the system and follow proper lockout/tagout procedures to prevent accidental energization. Use appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. When making connections, ensure that they are clean, tight, and free from corrosion. Use approved connectors and terminals that are properly rated for the application. After completing the corrections, thoroughly inspect the installation to verify that all work has been performed correctly and that the installation now meets the requirements of the National Electrical Code. Use a multimeter to measure the resistance of the grounding system and to verify that all bonding connections are secure. Document all corrections that have been made and keep a record of the inspection results. This documentation can be helpful for future reference and for demonstrating compliance with code requirements. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. If you're not comfortable performing electrical work, it's best to hire a qualified electrician. In summary, correctly identifying the service point and service disconnecting means is crucial for proper grounding and bonding. The neutral and grounding electrode conductor must be bonded at the service disconnecting means, and the grounding electrode conductor must be properly sized and protected. All metal enclosures and raceways must be properly bonded together to ensure electrical safety. By following these guidelines and consulting the National Electrical Code, you can ensure that electrical installations are safe, reliable, and compliant with code requirements. The importance of proper grounding and bonding cannot be overstated. A well-designed and properly installed grounding system protects people from electric shock, minimizes the risk of fire, and helps to ensure the proper operation of electrical equipment. It also provides a path for fault current to return to the source, allowing overcurrent protective devices to quickly clear faults and prevent damage to the electrical system. Therefore, it's essential to take the time to understand the principles of grounding and bonding and to follow all applicable codes and standards when installing or inspecting electrical systems. The NEC provides a comprehensive set of rules and guidelines for grounding and bonding, and it's important to be familiar with these requirements. In addition to the specific requirements mentioned earlier, there are several other important considerations for grounding and bonding. For example, the grounding electrode conductor must be continuous and unbroken from the service equipment to the grounding electrode. Splices are not permitted in the grounding electrode conductor unless they are made using reversible compression connectors or other approved methods. The grounding electrode must be located as close as practicable to the service equipment. This minimizes the length of the grounding electrode conductor and reduces the impedance of the grounding path. If multiple grounding electrodes are used, they must be bonded together to form a single grounding system. This ensures that all parts of the electrical system are at the same electrical potential. In some cases, it may be necessary to install supplemental grounding electrodes to improve the effectiveness of the grounding system. This is particularly important in areas with poor soil conductivity. When installing supplemental grounding electrodes, they must be spaced at least 6 feet apart and bonded together with a bonding jumper. The size of the bonding jumper must be in accordance with NEC Table 250.66. It's also important to consider the impact of other electrical systems in the grounding system. For example, if there are separate derived systems such as generators or transformers, they must have their own grounding systems that are independent of the service grounding system. This prevents circulating currents and reduces the risk of ground loops. Ground loops can cause noise and interference in sensitive electronic equipment and can also create a shock hazard. To avoid ground loops, it's important to isolate the grounding systems of separate derived systems and to use shielded cables and connectors for signal circuits. When working with electrical systems, it's always important to be aware of the potential hazards and to take appropriate safety precautions. Always disconnect power to the system before beginning any work, and use proper lockout/tagout procedures to prevent accidental energization. Wear appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. Never work on electrical equipment while it is wet or damp, and always follow the manufacturer's instructions for installation and maintenance. If you are not comfortable performing electrical work, it's best to hire a qualified electrician who has the knowledge and experience to do the job safely and correctly. By following these guidelines and taking the necessary precautions, you can help to ensure the safety and reliability of electrical installations. Proper grounding and bonding are essential for protecting people from electric shock, minimizing the risk of fire, and ensuring the proper operation of electrical equipment. The National Electrical Code provides a comprehensive set of rules and guidelines for grounding and bonding, and it's important to be familiar with these requirements. Always consult the latest edition of the National Electrical Code and local electrical codes for specific requirements and guidelines. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. In the described scenario, the contractor needs to address the following deficiencies to meet code requirements. Firstly, the neutral and grounding electrode conductor must be bonded at the service disconnecting means, which is the breaker in the meter can. Secondly, the grounding electrode conductor must be run in an approved raceway or other approved means, not EMT unless properly bonded at both ends. Thirdly, the grounding electrode conductor must be properly bonded at both ends to the breaker and to the grounding electrode outside. By correcting these deficiencies, the contractor can ensure that the electrical installation is safe, reliable, and compliant with the National Electrical Code. Understanding the roles of service points, service disconnecting means, and grounding electrode conductors is essential for anyone involved in electrical installations, whether it's for residential, commercial, or industrial applications. These concepts are fundamental to ensuring the safety and reliability of electrical systems and protecting people from the hazards of electricity.